Cool. Okay. Can everybody hear me? Okay. Let me just, great. Okay. Hey, I'm Kathy Wong. I'm a graduate student in the Computational Cognitive Sciences group at MIT. And I'm actually jointly presenting on this work with Katie Collins, who's joining me via Zoom. And it's work done with a whole host of really wonderful collaborators, a lot of whom are in the back of this room. Okay, so I wanted to open this talk with actually a really basic and fundamental observation. And this was actually a really fun slide to make as someone who really loves language, which is that we as humans use language to express a really broad and rich range of our thinking, right? We can talk about language, which refers to things that are out there in the world, like these scenes. We can tell stories. We can pass on observations that other people might have told us and that we've only heard to be true. We can convey information that's just purely imagined. We can give instructions for goals that we know and pass on our kind of personal plans. And we can give explanations for latent causes, things that we might observe in the world, and provide information that other people may need. And so I think in the background, lurking for any kind of computational model that deals with language, or at least human language understanding, kind of a general overarching question is, what kind of model is going to be sufficient to explain how this kind of wealth and breadth of language relates to human thought, right? How do we make meaning out of it? How do we produce it in all of these kinds of different ways? So here's one approach. It's kind of a classical approach. It unites a lot of theories, like classical cognitive theories that we have a language of thought, or many different kinds of linguistic semantic theories, or even NLP approaches like semantic parsing, right? Which is that we should maybe think about language as some kind of mapping from a range of different externalized forms, like sounds that we can produce with our mouths, or signs or letters, and some kind of structured internal representation, like a structured symbolic system. And that's what's the substrate of our thinking. That's what connects to all these different kinds of interfaces like perception or motor action. But even acknowledging all of the different work that's been done across all these different traditions, I think arguably in many ways, this kind of elegant idea has yet to cash out on its general promise, right? Where is that general meaning function if we want to actually computationally implement it? That's sufficient to kind of describe and span that breadth of real language in all of those different domains that I showed in the opening. And I think it's in many ways actually because of that want for breadth and scale. Actually, I'm saying this kind of with my AI hat on, that we've seen, especially recently, support for, or I think at least great interest for another approach, and that's what appeared in all the different talks that I think we saw this morning. And this story, I think, which is appealing because of its generality, is that actually a certain kind of model, which we might think of as like an extremist version of the purely distributional approach to semantics, which is a sufficiently expressive kind of arbitrary function that's just a predictive model over the distribution of next words on language, is actually going to be sufficient to come to do something more than just predicting language alone, right? There's kind of, especially if you've been following along the AI literature recently, a lot of interest in probing whether these kinds of models are kind of coming to emulate a more general substrate of reasoning. So not only the kinds of like situated learning things that Andy talked about this morning, or the kinds of object semantic features that we saw earlier, but asking whether these kinds of models are coming to show, generalized planning abilities for arbitrary goals, whether they contain enough information to reason about arbitrary physical common sense reasoning, even whether they are capable of kind of long-term quantitative reasoning about mathematical problems. And all of this is supposed to be perhaps something that's emergent and maybe even symbol-like, but comes actually only out of the latent structure that's sufficient to just predict the next word across distributions learned from human language. So in this work, we actually break it down into kind of two parts. And so in the first part, I think in some ways we want to kind of push back against that view and present a benchmarking experiment that suggests, well, if you just think about what these models are doing, which is learning distributions of text, you might expect that there are going to be classes of problems that they might struggle with, in particular ones where we start to deviate kind of the underlying problem from the typical distribution of language. And so this first experiment is kind of a systematic approach for constructing some of those and presenting some kind of evocative results. And this is done with kind of the state of the art in generative language modeling with GPT-3. In part two, I want to go through, I think, what's a simple model, but I think hopefully an evocative one of a class of approaches that we might take that in many ways, I think is just actually like a fresh look at that classical approach, but with kind of this modern computational toolkit. And it talks about another way that we might see these kinds of distributional models as integrated with something that we might think of as kind of a modern instantiation of a classical symbolic structured language of thought. So let me talk about part one. So in this benchmarking experiment, we look at two different domains that people can really readily talk about in language. So one of them is coming up with and describing plans or sequences of actions that achieve goals, which we can express in language. So here's a few examples of the kinds of goals that we ask people. And the kinds of answers that they can give us, right? And you see that people are kind of flexibly able to answer a host of different goals. We can tell you how you clean dirty dishes. You know, a strange number of people know how to escape quicksand, or stop your canoe, right, from falling down a waterfall. And here's a few more examples from the other domain that we use. It's this causal explanation domain. And so if you look at all these different kinds of prompts, we take kind of this premise and violation approach so that people can give kind of a concise, single, intuitive causal answer. And these are a few of the example explanations that people provide, right? They can think about things as varied as why rocks thrown in a window might not break, to why when plants are watered, maybe they might not die, which I'd like to know too. And, you know, because this is language, we can ask a large language model, which I just said is, in this case, the state-of-the-art GPT-3 model that appeared in some of those other works, to try and like solve these problems, right? We can ask whether it's reasoning about these problems. And we can frame that as a kind of language prediction problem, right? We just give the model these questions and we allow it to just predict the next token that would come next. And for these kinds of initial problems that are actually taken from our experiment, right, here are just a few sample responses that it predicts. You know, these responses, I think at first glance, they actually appear pretty reasonable. They look a lot like the things that humans said. But I'm going to focus on planning as a running example, but as you'll see, we do this in explanations as well. Kind of the hallmark, right, I think of what we think of as the flexibility of human cognition, and maybe specifically as it applies to planning, is that it's not limited to a particular situation. I think we have models of the world that allow us to adapt and to think kind of reason robustly about the underlying problem that this expresses. And so in this little paradigm, what we do is we solicit human responses as a kind of, you know, coarse estimate of the kinds of typical answers that it is that people give. And then we take that initial prompt and we actually elaborate on it. We generate these new and kind of more constrained versions of each prompt that rule out kind of typical elements of the solutions that people produce. So we produce in one condition, we elaborate on that goal prompt with by constraining out the most common means, I guess, that people use. So in this case, you know, a bunch of people say to use an or. And then one more kind of hard condition that rolls out actually all of the named means that people gave in that initial condition in language. And when you ask people about these kind of elaborated prompts, a new set of subjects, they can actually readily kind of adapt to give new plans for these constrained goals, right? So in the first case, if they can't use an or, you know, maybe they figure out that something like an or, you can use your hands to paddle. And in the last case, we've kind of pointed out a bunch of times, you might notice that in a bunch of ways, this is kind of like a weird reframing of the problem. Like technically, if the canoe has sunk, it won't fall down the waterfall. But it's still one that I think in many ways you can see meets key parts of that criterion, right? And it's subject to all the different constraints that we laid out. But when you subject large language models to the same task, and once the language, or I think really the underlying problem, is no longer in distribution, you see that these plans that they produce start to break down. And I think if you look at them, you can see that they actually start to break down in kind of more fundamental and meaningful ways than in the human case, right? So without using an or, digging your feet, like what is the side of a waterfall? You know, and in this case, I think either it seems almost like impossible, physically impossible to do what the model is saying to do, or it just feels like there's no way in which a plastic bag is going to have any kind of meaningful part of this plan. Right, so what might be missing? I think, again, if we just go back to what it is that this model is trained to do, you might suspect that there's actually a host of different things, right? Maybe it's missing kind of a true structured world model of this problem. Maybe it's actually not really compositional fully over all these different constraints that we provided. Maybe it lacks kind of a coherent way of causally rolling forward what happens in the world, given all these different actions and events. And here's another example from our planning domain. You can see that in the first case, I think it's almost giving kind of the opposite of what it's supposed to do. If you threw the rocks harder, they would almost more likely break the window. In the second case, I don't know why it's so fixated on the rocks being frozen, but it actually gives that example in like a bunch of different answers. So it's not just one instance. And indeed, if you ask real humans to kind of do the Turing test-like comparison that I think someone brought up earlier, right, where they're actually rating these plans for each goal side by side and they don't know who generated them, you can see that for the kinds of goals that people, or the kinds of plans that people answered, and that's the ones in blue, as these goals get more constrained, conditioned on that goal, actually the human plans, right, they're not getting worse. The scores just roughly aren't going down. And then for the language models, which are in gray, you can see that humans start out thinking that they're roughly like humans, but then they deteriorate right, much more rapidly as we add in more and more of these constraints. And you see a similar kind of pattern in the explanations domain as well, right? People's explanations in blue are relatively constant. The large language model just deteriorates really rapidly in gray as we add more of these constraints. Okay, so originally, sadly, I was going to hand it over to Katie Collins to talk about part 2, but now it's just me. We're going to talk about kind of an alternate approach, I think, to answering these kinds of problems, where we're not actually asking these large language models to reason in and of themselves, but I think rather tries to integrate them, again, just as what they are, which is rich statistical models over the distributions of language. And here uses them as kind of hopefully a more modern approach for getting structured representations of the meaning out of language that we can reason over. So for the purposes of this experiment, we actually focus on only one of the 2 domains, on planning. And we look at this really simple, but I think, as you'll see, quite actually flexible and non-trivial domain. And it's one that's actually very well studied in the AI and planning literature, and in particular, one where we can actually really systematically formalize the planning problem that we're asking completely and also specify in language. And these are these object stacking problems. So in all of these problems, we're talking about a finite set of objects that are in some initial configuration. You can imagine them as if they're on a table. And the goal is to produce some kind of final configuration that's described in language based on the relative locations of all the different objects stacked in some order. So here it's saying that the laptop is on the table, the novel's on the laptop, you can go on and talk about all the different things. And the goal was at the end that so it was on top, now the novel is on the table. And this is kind of a simple domain, but it can be made easily kind of arbitrarily complicated, right? It predicts, or it permits a lot of different variation based on the initial configurations, as well as like all the kinds of different elaborated goals that you can come up with, different kinds of configurations. And for all of these kinds of goals, right, you can express a plan in language using just a few simple actions that we can model completely, right? Namely, picking up objects off of an object, then placing them down on some other kind of object. And so again, right, in this domain, we can actually try and get a large language model to solve these planning problems by just asking it to produce a series of actions directly in language by predicting the next word. And it's actually very straightforward to constrain the large language model to use words that correspond to the specific set of actions. So we do that, like pick up and put down. But again, from part 1, you might start to suspect that as the problems grow more complicated in general, even in this simple object stacking domain, things are going to start to break down in coherence, like we saw earlier. And so here's kind of the simple alternate approach that we take to solving these problems, which uses that large language model as a component of language understanding, but for a task that we think doesn't require to really emulate the general reasoning in this kind of task, and which I think in many ways is a lot better suited to a model that you might think of as learning really like sophisticated patterns, right? Mappings over the statistical structure of language. And here that's essentially to act as a kind of semantic parser, a general kind of statistical learn function that maps from natural language into a structured logical form in a rich kind of symbolic language of thought that expresses its semantics. In this case here, we use kind of a classical planning programming language, PDDL, that expresses just propositions about where things are, right, and its goal state. And here, by the way, we're actually using a variant of a large language model that's trained specifically on joint distributions of natural language and code. Oh, I'm almost done. Okay. And one way to think of the model here might be as kind of, I think, like an amortized mapping function, right? A parsing function from surface forms to logical forms that's translating between the space of language and programs. But the key is that we're not actually asking it to do the underlying reasoning. Instead, to actually solve the problem, we don't use it to do generalizable reasoning. We use this kind of symbolic model-based planner that can work actually backwards deductively from the goal to figure out a sequence of actions that satisfies those propositions. And then in this toy domain, we can do something analogous to the first set of experiments, right? We can take those initial sets of goals and we can build kind of more elaborate constrained versions of them that add on different constraints. And indeed, when we compare our model, which is in purple, to the large language model baseline in gray, we see kind of a similar pattern, which we might have expected from part one, right? This kind of structured model, which uses an actual symbolic language to reason, remains relatively robust as these goals grow more constrained. And the gray model deteriorates so rapidly that actually in the last most constrained condition, it wasn't solving any of the goals. And we started to wonder whether maybe our sample size actually wasn't even large enough to really draw out this effect. And so, taking stock of part one and part two, our experiments first highlight that maybe these distributional language models alone kind of fail to capture, I think, the human-like robustness that we associate with actually reasoning about the underlying content and semantics of language. But our work in part two, I think, offers kind of an alternate way that we might think about these models as kind of integrated into a classical kind of notion of what it is that language is, kind of a mapping from these kinds of surface forms into some kind of structured symbolic language. So wrapping up, where do we go from here? I think there are a lot of open questions that many of which we're actively exploring now. I think one obvious one is, how is it that we generalize the model that we showed, which was just on planning, across these other kinds of domains that we can express in language, like in the introduction, or even just the explanations that were in part one? I think two other questions that this raises are, one, right, how does that kind of distributional approach that we're using as a semantic parser relate to kind of classical theories of linguistic meaning that I bet are familiar to a lot in the audience, right? Kind of formal compositional semantics, even like the one in the talk that we just saw. And finally, I think an open question, if we were to think of this as actually some kind of approximation to a cognitive model, is, we want to talk about how actually a human being could come to learn this kind of distributional mapping function if we think that something like this is at play from realistic amounts of linguistic data. We know that people aren't trained on billions and billions of, tokens of text combined with some kind of observation, even multimodal observation. So we need kind of an explanation for that. Thank you to many of you guys. Many of you are here. If there's any time, I can take any questions. But thanks.
We've got about 5 minutes, so